Hello and welcome to today's lecture. Today we will take a look at a certain phenomenon that appears when we talk about planar graphs and plane graphs. That phenomenon, known as duality, has a very geometric, concrete way of constructing it, but also an abstract meaning. And it is an example of a general phenomenon that appears in many areas of mathematics. But let's not get ahead of ourselves. Let's start with this concrete question. So if you take a cube and you pick a point in each face of the cube and you connect 2 points with an edge or a line or a curve, precisely if the faces share an edge of the cube, what geometric figure do you get? So try this and pause. Well, the answer is you get what is known as an octahedron. It's a different polyhedron. And now that's exciting if you like octahedra, but if not, maybe let's try to produce something new. So let's start now with an octahedron and do the same thing. You pick a point in each face and you connect 2 points if they are on faces that share an edge between them. What do you get? Try this, pause the video. Welcome back. So let's do this, but mind you, I am horrible at drawing and also it's not clear which faces I am doing this with. But if you somehow believe me, and hopefully you have better drawings yourselves, you will see that what you get is something much akin to a cube. And if you do this properly, you'll see that you will get a cube. Maybe distorted if you choose the points a bit up or down, but still the same geometric shape as a cube. So that's kind of interesting. We started with a cube, did something and got an octahedron, then we did the same thing. We didn't undo what we did the same thing again to an octahedron, expecting some new exciting shape, and we got the cube back. So it's somehow a procedure that repeats after 2 steps. And from the Latin word for 2, we get the word dual. And what we want to say is that the cube and the octahedron are somehow mirror images or duals of each other. So this hopefully gave you some intuition of what happened, but it's a bit ad hoc and not very precise. So let's make this precise. So, as you might remember, we had a way of looking at polyhedra as plane graphs or planar graphs. So what we're going to do is we're going to construct this graph theoretically in terms of plane graphs. So you take a plane graph G and you want to construct another plane graph G star. Remember, a plane graph is a graph that is already drawn in a plane in such a way that no edges cross each other. So how do we do this construction more precisely? So we need to construct a graph, meaning we need to construct vertices and edges. So as the vertices, you pick 1 point in each face of your original graph G, and you connect 2 such vertices precisely in such a way that you cross exactly 1 edge of your original graph. So for each edge of the original graph, you draw a curve, crossing that edge and nothing else, and connecting the corresponding points in the corresponding vertices. So how does this look? This is our plane graph. It has 3 faces, this triangular face, this rectangular face, and the infinite face. Very good. So now I have my vertices. So what I'm constructing is this G star. Okay, so now this is an edge in G, and I want to cross it with some line or curve connecting the 2 vertices on each side. This is another edge. I do the same thing. This is an edge. Now also this point and this point, their faces share this edge, and they share this edge. which edges have I not crossed? This edge I have not crossed. It goes from this vertex to this vertex, and same. So I repeat this for all the black edges to get my red edges. And now I have that. And this edge is left. So this edge is entirely immersed in the infinite phase, but that's okay. So both faces in this on both the faces on the both sides of this edge are the same. So my red edge will go from the same vertex to itself. And this is the construction that gives me this kind of horrendous graph G star. So a few things to observe. Because of what I said last, this edge that leads to an end vertex, a vertex of degree 1, will give me a loop, because such an edge will be entirely immersed in the face it is in. And also, if this was a path of, say, 5 edges leading up to an end vertex, then I would get 5 loops. Also, if I have two faces with several edges between them, then I will get multiple edges in my red graph G star. Why is that? Well, because I'm going from the same vertex to the same other vertex, crossing several possible edges. So I get red edges, more than one red edge between the same vertices. The third thing to observe is that actually this G star is entirely determined by G. I didn't have much choice. The choice I would have had is maybe this vertex, instead of placing it here, I could have placed it somewhere else in my rectangular face. But really, this just distorts the graph a bit and still gives me something that is isomorphic. So to put these together in writing, end vertices give loops. Two faces sharing more than one edge give multiple edges. And the red graph G star is uniquely determined by the original graph up to isomorphism, since we get the same number of vertices and the same vertices will be adjacent to each other, and then by definition the graph will be isomorphic. So this graph G star has a new name. It's called the geometric dual of G, and it's determined by G, so it is justified to call it the geometric dual of G and not a geometric dual of G. And remember, for this to work, we started with an actual plane graph, like an actual drawing in the plane of a planar graph, not some abstract planar graph. We will deal with that situation later, but this procedure gives us a way to construct G star from a plane graph G. So now that we have constructed this new plane graph G star from our original plane graph G, let's try to find some interesting facts about this graph G star. So the first fact is about the numbers of vertices, edges, and faces. So if G has n vertices, m edges, and f faces, then G star is going to have the same number of edges as our original graph G, as many vertices as our original graph had faces, and vice versa, as many faces as our original graph had vertices. Why is that? Well, let's call the number of vertices, edges, and faces of G star n star, m star, and f star. So the number of vertices in our new graph is the same as the number of faces in the original graph, just because of the construction. I put exactly one vertex in each face. And the number of edges is the same as the original number of edges, just because, again, of construction, for each edge I drew exactly one edge crossing exactly this edge and nothing else. Now, using the formula of Euler twice, so I know that my dual graph G star is plane, a plane graph. So then Euler's formula applies, and the number of faces in the new graph is the same as 2 plus number of edges minus number of vertices. But now I've already told you that the number of edges is the same as the number of edges in the old graph, and the number of vertices is the same as the number of faces in the old graph. So I get 2 plus m minus f, which are the numbers of edges and faces in my old graph. And using Euler's formula now for the old graph, which was plane, I get n. So this shows that the role of faces and vertices are somehow interchanged. Edges correspond to each other still. So now we have this numerical fact about the dual. Let's look at another property. What happens if we construct the dual of the dual? So you have a plane graph G. You do this construction, you get G star, which is also a plane graph. Now if you do the same thing to G star, what are you going to get? Well, from the octahedron cube thing, we expect to get G back, and indeed this is what happens. So G star star is isomorphic to G. Why is that? Well, let's try to construct G star star. So how do we do that? Well, let's first draw an example. So let's draw here. Assume that this is my G, and then my G star will be this red graph. So 2 vertices, one for each face, and one edge crossing each edge. So this is my G star. And now I repeat the same to get G star star. So now I need to pick a vertex in each face of G star. This is supposed to be G star. So in each face of G star, you will find exactly one vertex of the original graph G. Why is that? Well, because each face of G star is surrounded by edges of G star. So since the edges of G star are only put there to cross edges of G, this means that to each face of G star, in order to be surrounded by edges of G star, it has to have edges of G going into it. And the only way to have edges going somewhere in a graph is if there is a vertex there. So there has to be at least one vertex of G inside each face of G star. And there cannot be more, because from the previous slide, we know that the number of vertices of G equals the number of faces of G star. So if there is at least one, there has to be exactly one. So I can pick the vertices of G as my vertices of G star star. And then by construction of the edges of G star, there is exactly one edge of G star crossing each edge of G and no other edge. So conversely, there is exactly one edge of G crossing each unique edge of G star. And I can take this edge as my edge of G star star. So this edge, then I can take this edge, and then this, let's maybe not take exactly the edge, let's shift it a bit. But still, I mean, apart from moving vertices around or drawing edges a bit curved, it's exactly the same graph. G star star is isomorphic to G. So to summarize, we have at least one vertex of G in each face of G star, because being surrounded by edges of G star means that you have edges of G coming into it, and at most one by the count of the proposition on the previous slide. And so we can pick the vertices of G as our vertices of G star star, but that's not enough for isomorphism, because we need also to show that the adjacencies are the same. But by construction of G star by these unique edge crossings, we get exactly one edge of G star star for each edge in G, because in both cases we have a unique edge crossing in the construction. So this concludes this theorem, which has the wonderful advantage that we never have to talk about G star star again, because it's horrible to say, and also because it's isomorphic to G.